Hello, and welcome back to the second part of Chapter 6 for this week. So we're going to pick it up with a sampling distribution of a proportion, so that P bar is the point estimator of the population proportion P, which is the overall proportion of the actual population. So the formula for computing that sample proportion is the number that meet the criteria divided by your sample size. So the expected value of P of the sample is equal to the proportion of the population, and then the standard deviation of P proportion sample, P bar, is equal to, and that should look familiar, n minus the small n and the n minus 1, take the square root of that and multiply it by this value here of the proportion times 1 minus the proportion divided by n, the square root of that. That's for a finite population, and then for an infinite population it would just leave off the error here coefficient and just do P times 1 minus P divided by n, take the square root of that. And that'll give you the standard deviation for the proportion of the sample. So here's what that distribution looks like for that proportion. The expected value of P bar, 60%, the standard deviation of 0.0894. So the sampling distribution of P bar can be approximated by a normal distribution, and that's what we want again, when n times the proportion is greater than or equal to 5 and n times 1 minus p is greater than or equal to 5. So if we meet those two criteria here, then we can say that that sample distribution of that proportion is normally distributed. So the next thing we want to talk about is interval estimation. So we want to do interval estimation of the population mean and the population proportion. So think of interval estimation as we've seen that when we take a sample and it's not exactly what the population mean is or the population proportion, but we'd like to have some estimate about how close are we. Are we within 5% of that or 2.5% on either side, so that we can be fairly confident that we're close to those population means and population proportions. Once we know that we're fairly fairly used or close to those population means, then or population proportion, we can make some generalizations about the population, about what we're studying. And so because that point estimate cannot give us the exact value of that population parameter, we'll typically have an interval estimation to generate an estimate of the value of the population parameter. So that interval estimate typically will add or subtract a value. That value is called the margin of error to the point estimate. So in the previous slide I said, well, what if it's 2.5%? So the margin of error might be 5 if it's plus or minus 5, or plus or minus 2.5. So you have what you actually estimated plus that margin of error. So for the population mean, it's the x bar plus or minus the margin of error. And for the population proportion, that interval estimate is that sample proportion plus or minus the margin of error. And that gives us some estimate of how close we are to the actual estimate, point estimate that we're talking about. So some numbers that you should keep in mind when we talk about a normally distributed random variable. 90% of the values lie within 1.645 standard deviations of the mean. 95% of those values lie within 1.96 standard deviations from the mean. And then 99% of the values lie within 2.576 standard deviations from the mean. So this should go back to what we looked at, a normally distribution, and we did our estimates. And we said that if it's after or further out than plus or minus 3 standard deviations, then that was probably an outlier, and we should take that out of our data set, or at least examine it more. So here we have a distribution showing 1 standard deviation. So if we look at that, we can see that if we do a bunch of random samples of 30, where do each one of those means for those samples lie? And that's what this is showing here. And we just said from the previous screen that we should get 90% of our values will lie within 1.645 standard deviations. So if we look at our standard deviation is equal to sigma divided by the square root of n, then that's what we've got here. I'd also like to point out that these values come from z-scores. So it should be something we've seen before. Another thing you should understand about interval estimation is that sampling distribution, when it follows a normal distribution, that the uncertainty by using let me say that again, that when the sampling distribution follows a normal distribution, the additional source of uncertainty by using a probability distribution is known as the t-distribution. So it's a family of probability distributions. So the shape of each specific one depends on the number of degrees of freedom. But that shape of that t-distribution, similar to a standard normal distribution, but a little wider. As the degrees of freedom increases, that t-distribution narrows, and the peak becomes higher. And that's when it becomes more similar to the standard normal distribution. I mentioned the t-distribution because when we get into the latter half of this chapter, that's where we're going to do our hypothesis testing. And we need to understand where our point estimators lie in that distribution. Can we say with confidence that certain things are equal or certain things are not equal? And that's what we're using. And this is just some of the background, the theory behind being able to do that hypothesis testing. So here's an example of standard normal distribution. Then we have a t-distribution with 20 degrees of freedom, and then a t-distribution with 10 degrees of freedom. So notice how when you go up in degrees of freedom, the peak gets higher and it gets closer to a normal distribution. Also notice that the standard distribution is a black line here, and so the t-distribution is slightly wider than the normal distribution. So using a t-distribution for our sample, we can use a function in Excel called t.inv.2t function to find the value from a t-distribution, so that from a given percentage of the distribution is included in the interval plus or minus t for any degrees of freedom. So I've already plugged that in for you, and you'll see my formulas here, and we can just do that again. So I want to know where in my sample do 90% of the values lie. So if I do equals t and I go and do this function, so it returns the two-tailed inverse of students' t distribution. So I'll use that. It says do a probability, and the book shows 1 minus 0.9, or I could put in 0.1 there, do the calculation ahead. And then the degrees of freedom. Well, we have 30, it's our sample size, and we need to do n minus 1. So our degrees of freedom is 29. So you can see where the sample size minus 1 gives you your degrees of freedom. So that's telling me that 90% of my values lie within plus or minus 1.699 standard deviations. Okay, that also tells me, if I look at this one, that 10% or 5% on each side of that mean do not lie within that range. So if we look at, let me move this out of the way. This, we can see that we can use those intervals around our sample mean. So we have whatever our sample mean was here minus that calculation or plus that calculation. So this one lied within it, this one did too. We have an outlier here that this particular mean from that sample does not lie within that standard deviation, and we can look at the rest of them. Now, what I was saying earlier in the slide, you want to look at figure 610 here. And so that slide, what it's showing there, let's see if I can draw this out. That you've got a little more tail out here, and that in that tail, that's 5% here and 5% here, right? Because it was what's covered here is the 90%. That's what we calculated on. And so when you do that calculation, what you can then say about the population mean, so if we know that approximately 90% of all the intervals constructed will contain that population mean, we can say that approximately 90% confident that the interval will include the population mean. So we're 90% confident on most of these. Well, we would say we're 90% confident on all of them, that contains the population mean. And you can see that all the lines are crossed except for one. So that becomes one of those outliers that it didn't lie. We've got the mean, and then we take our interval. It didn't, in that interval, it didn't lie in the mean. And so it doesn't happen very often, but it does happen because we're only 90% confident here. So some more terminology here is that value of 0.9 is referred to as the confidence coefficient, and the interval is called a 90% confidence interval. The level of significance is the probability that the interval estimation procedure will generate an interval that does not contain the population. So alpha is the level of significance. 1 minus alpha is the confidence coefficient. So that's what we were entering into the Excel formula. 1 minus the confidence coefficient. So here our level of significance is 10%. That 10% is a two-tailed test, so it's split in half. So 5% goes in the plus side of the mean, and the 5% goes in the negative side of the mean. So now we have something called the interval estimate of the population mean. So that's going to be, again, what we calculated as the sample mean plus or minus T alpha 2 divided by 2 times S divided by the square root of n. And so it tells you what all of those letters mean below. So S is the standard deviation, N is the sample size, and you will have a degrees of freedom of n minus 1. So here's an example of some credit card balances for a sample of 70 households. And we'd like to construct an interval estimate for the population mean. So what we like to say is we sampled 70 households, and we'd like to be 95% confident that the mean of this sample is the same as the mean of the population of households. And we can get Excel to help us do this. And when we run the numbers, we can run it for 95% confidence level. And notice it gives us what the point estimate is, what the margin error is for 95% confidence interval. And we can calculate the min and the max and a point estimate here again. So the min of these new balances are listed here. So let's go ahead and show that. So what we'll need to do is we'll need to make sure that we have our descriptive statistics from the list of analysis tools. So we need to make sure our analysis tools is on. So typically that's one of the first things I do when I get into Excel. This is the same data, I just pulled it. The book gives you the name of the file is New Balance. So to make sure you've got that pack installed, you go under File, you go under Options, and then you'll need to scroll down, go to Add-ins, and then at the bottom of the page, you'll see where it says add-ins, but you could also do other type of add-ins, but we want the Excel add-in. We'll hit go, and then you'll see that there's a check mark right next to the analysis toolbar. If it's not on your machine, then you need to make sure that's checked, and that'll be installed for you. Okay. So now we can get back into Excel, and we can run through what it says to do in the book. I'm on page 245. So we click the Data tab. We go to Data Analysis. All right, so that's over here. See Data Analysis in the Analyze group. And we can select Descriptive Statistics. We'll click OK, and now it's going to ask us for some information to fill in. So the input range is going to be where our data is. And so our data is going to be, we click here, we're going to select A1 to 71. And we're going to group by columns. Our first row did contain a label. Our output range, that's where we want the descriptive statistics to go, is we're going to say the output range is going to be C1 here. So that just needs to be the upper left-hand corner of the box that's going to be produced. We're going to select summary statistics. Our confidence level is going to be by default 95%, or we could change that. And when we're done, we'll click OK. When we click OK, we might have to widen some cells to see everything. You can see that it produces the same results that are in your book. Now if we want them to be different color, we can set that background color to go to the Home tab. We could do orangey color. All right. So that's how easy that is to do. You didn't have to do any calculations, and works out very nice. So notice how we get the point estimate down here. This is what you're actually calculating. So that's this value here. That's the cell reference. The lower limit is D18 minus D16. So D18 is this value, or this value again, minus D16. D16 is our confidence level. So it's 955. And the upper limit would be D3 plus 955. And this is at the 95% level. So what we're saying is we're confident, and 95% confident, that 9,312 is within this range of a lower limit to upper limit for the actual population given this sample. So what about proportion interval estimation? So it works the very similar, very same way. So the interval estimate for a population proportion is this formula. Again, where alpha is the level of significance, z value providing an area of alpha divided by 2, that's this area z, in the upper tail of a standard normal distribution. So upper tail means that alpha is for 2 tails, you divide by 2 to get the ending tail of each one. So that's this area here, what I was talking about. So the proportion for this interval estimation is right here, and then minus that calculation or plus that calculation. And if you look in your book, you'll see that we can get those values in a spreadsheet. Notice we have to use count A because we're not counting numbers and we're looking for yes or no. We can count those responses, count if in that range, and we're looking for a value of this cell, D4. The sample proportion then is that D5, which is our count of responses, divided by our sample size, which are 0.44. Okay. If we're going to use a confidence interval of 0.95, so our level of significance is going to be 1 minus that 0.95 or 0.05 here. Now we're going to get a z value out of this. And so the function to use for Excel is norm.s.inv. And 1 minus our level of significance divided by 2. And so our z value here will be 1.96. And that should sound very familiar because I mentioned it earlier where those numbers came from for 90%, 95%, and so on. Right. Our standard error then would be the square root of D6 times 1 minus D6 divided by D3. So that should look familiar, which is this formula here, I believe. All right, our proportion D6, which is right up here, times 1 minus D6 divided by our sample size, and we take the square root of all of that. So then our margin of error would be this z value times our standard error. And then, so we can then get our point estimate. Again, that's going to be D6. That's the sample proportion. Now, what's the lower limit? That's going to be our value minus D13, which is our margin of error. We showed you how to get that. The upper limit is our value, our point estimate, plus that margin of error. So these are the values that you see over there. So that means for this proportion of 44%, we're within these limits of either 40% or 47%, we're 95% confident. And so I hope that will help you as you work through some of the problems for this next week. And so the following week, we will then cover the rest of the chapter, starting with hypothesis tests.